Welcome to the part B of lecture 7. We are going to now talk about class of ill-posed problems. Class of problem is known as ill-posed if either they fall into either of the three status or three features. If you see, one is there will be a unique solution does not exist for a problem. Second is unique solution exists but computationally not feasible. You have a unique solution but computationally it is not feasible. Computationally finding a solution is impossible. And the third possibility is unique solution exists but the solution is highly unreliable. Now I will give you three examples of all three cases. First example is, this is the example 1, problem of variable selection for large P and small n. If you have a design matrix with n cross p and the number of column is more than number of samples, then the number of feature is more than the number of samples, then what happens is X transpose X is not invertible, as we have seen in the previous part of this lecture. Since we don't have any unique solution, this is considered as a ill-posed problem. Second example is the problem of variable selection, particularly for very large P. So you have P is so large that the model complexity becomes too high, and searching through all the model complexities become almost impossible. And the third problem is you have a solution but you can compute it, but your solutions are unreliable, and multicollinearity is a good example of such problem. All these three types of problems are known as class of ill-posed problems. First we will talk about class of ill-posed, first class of ill-posed problems where unique solution does not exist at all. Particularly problem for variable selection in large P small n setup considered as an ill-posed problem. Such problems are very common in medical sciences. For example, in a study of the efficacy of a treatment, suppose the study randomly choose to observe 100 patients. It means the sample is of size n equal to 100. So n equal to 100. Now scientists run thousands of tests, and for each test on the patients, say from regular glucose level to genetic marker, anything and everything that is possible, and collect the results of those tests. Those are the features of the problem. Now P runs into 1000, so your n is 100 and P is 1000. And this is a very common scenario that you can find in the medical sciences. So we will find it very often. In such cases, what happens? In such cases, your X transpose X is not invertible. So that means you have infinitely, but normal equation has at least one solution. So that means in such cases you have infinitely many solutions. Infinitely many solutions. You have infinitely many solutions, and beta equal to 0 is also a solution. If beta equal to 0 is also a solution, what is the interpretation of it? It means that none of the feature you spend so much money to collect the results of those, glucose test and genetic marker, etc. None of these features have any effect on the treatment or the target variable y. It does not have any effect. So this is not a very desirable situation. So it is not the problem of the medical test. There is no biological or medical problem. It is just the model, the mathematical model that we are considering cannot address the issues, cannot handle this. So the model is inadequate in this scenario. In this, the model cannot address the large p small n problem. So this is a very common scenario that you will find in the medical sciences. Second problem is typically called problem 2 in the class of ill-posed problem. Unique solution exists but computationally not feasible. For example, you are running a variable selection in large P considered ill-posed problem for model complexity. Suppose you are working in a credit rating group where you are working with customer databases. The number of customers in your database is more than 100,000. So your N is 100,000. Okay. Each customer you have thousands of features. Your P is 1000. So theoretically you should be able to run a fit a model. Now if you run a simple stepwise variable selection, you have to fit 1 plus P into P plus 1 by too many models. That will be 500,501 many models. That is 500,000 model. So you have to fit 500,000 model to just run a simple stepwise variable selection. 500,000 model you have to consider. Forget about base subset selection. Just to fit a simple stepwise selection, stepwise variable selection technique, you have to fit 500,000 model. And each model you have to fit with 100,000 data points. So it is going to be a humongous computational facility you require. It may take several days to complete your job. And I am talking about, this is a very real life scenario. You can very easily run into this kind of problems. However, oftentimes in corporate environment, you do not have several days and upper management wants to resolve by the end of the day. And these are the scenario where theoretically you have a unique and good solution, but computationally finding the solution is not possible. You have a time budget. Your time budget is within 24 hours, you have to finish this work. But you have to go through 500,000 models to find the best model, and among the 500,000 models, each model has to be trained using 100,000 data points. So it is simply not possible. Given the computational facility, it is simply not possible to fit all these models. So unique solution exists. Now the third problem is unique solution exists but unreliable. So the problem of multicollinearity is a third kind of problem where you have a unique solution but it is unreliable. An interesting problem in the sense that you have a unique solution, however it is not reliable. So why it is not reliable? Because standard error becomes so large that you cannot do any reliable inference. You cannot do any reliable statistical inference. So how you solve it? So essentially these problems does not have a solution as it is. If this is the scenario, what you do is you regularize the problem. You regularize the problem so that you have a solution. And this methodology is called regularization. So you regularize the ill-posed problem so that you have a solution. And in this process is called regularization. We regularize the ill-posed problem so that we have a solution. This methodology is called regularization. Okay. The most popular is called Tikhonov regularization in 1943. Andrei Tikhonov, he was a Russian mathematician. He tries to find the solution for ill-posed problems by imposing certain restriction or conditions on the solution space. If a solution cannot be obtained, or if solution can be obtained, then we can say the process is regularization process of the ill-posed problem. How you find a regularization? You essentially penalize the objective function. You put a restriction on the parameter space of the objective function. That is how you do it. So how it works? So the class of function is controlled by explicitly penalizing the residual sum of squares of f with roughness penalty. What is it? So typically what happens is, how OLSS works, OLSs try to minimize residual sum of squares of the target function. That's how the OLS work. Okay, that solution is typically called OLS. So penalize this, we will still work with the RSS, the residual sum of square, but on the functions, on the objective function, we will put a penalty term, and we call it penalized residual sum of squares. Okay, and the amount of penalty will depend on the lambda. Lambda is typically called the tuning parameter. So if lambda equal to 0 means there is no penalty. If you put lambda equal to 0, and if higher the lambda, more the penalty. And typically lambda is estimated from the data. So we take fx equal to x beta generally, and residual sum of square of beta will be y minus x beta transpose y minus x beta. So this is the residual sum of squares of beta, and then we put a penalty term on the beta. That's how we typically work. What about penalizing L1 norm error? We can penalize L1 norm error. We can in this model, but for now we will focus on L2 norm error only. So we are not going to focus on L1 norm error. What penalty to choose? That always a interesting question. So the most possible choice is, popular choice is L2 norm penalty, that is P beta equal to beta minus beta naught transpose times beta minus beta naught. Now beta naught equal to choose 0, if you choose, that will be, this is typically L2 penalty. This is typically L2 penalty. Okay. So the analysis with L2 penalty is, so we want to penalize this L2 penalized loss, essentially y minus x beta transpose y minus x beta plus lambda beta transpose beta. And if we penalize this, so basically that will give us the Risdge solution. So if all we have to do, just penalize, just minimize this objective function. This is our objective function, and we just minimize with respect to beta, and the solution is called Risdge solution. So the equivalent solution is, equivalent construction is, you just minimize the residual sum of square essentially, but subject to this constraint. This also gives you the Risdge solution, same solution. Either you minimize this entire objective function, it is sort of a Lagrange multiplier kind of effect, you will see, or you just solve it as a constraint optimization. Here you minimize the residual sum of square subject to constraint beta transpose beta is less than equal to t. So it is something like that. What is happening here, if you look at carefully, what Tikhonov solution is doing is you put a budget on the total budget on the sort of on the beta, and if you put t goes to 0, if you put t goes to 0, then what happens is naturally many beta become shrinking. If the beta become shrinking, beta start going to 0. They typically shrink towards 0. That is what happens. Now, one can show that lambda here and t, they have a one-to-one correspondence between these two parameters, but generally there is no explicit mathematical expression, we have never found it. But one can argue that they will have a one-to-one function. Now, following the minimization problem, if you solve this minimization problem, the Risdge solution is x transpose. So you have an analytical solution, x transpose x plus lambda I inverse x transpose y. So Risdge solution is an analytical solution. It's an analytical solution. This is a very good news for us. Though I'm assuming if we know the value of lambda, then we can compute the Risdge solution for beta. So Risdge solution is a special case of Tikhonov solution. Next is LASSO regression. Least absolute, LASSO stands for least absolute shrinkage and selection operator, or LASSO. The LASSO shrinkage method, like Risdge, with subtle but different important differences. What is the difference? The difference is the penalty term. Instead of giving a L2 penalty, here they are putting L1 penalty, and rest of the thing is exactly same. So equivalently, you can show that you are trying to minimize the residual sum of squares subject to constraint this, and as same thing, you can basically, you are budgeting the total amount of beta. If you push the t towards 0, then all the beta will shrink towards 0. So LASSO does not have closed form solution like Risdge. LASSO, you have to solve it as a optimization problem. You have to solve it as an optimization problem. You cannot, unfortunately, you do not have an analytical solution. Computing LASSO solution is essentially a quadratic programming problem, turns out to be, and efficient algorithms are available for computing the entire path of the solution for different values of lambda. So with same computational cost as Risdge regression. So in that way, it doesn't matter much. So because of the nature of the constraint, making t sufficiently small will cause the coefficient to be exactly 0. Okay, thus what does it mean, sum of the beta? So if I have x1 x2 ... xp, and now suppose the beta 2 turns out to be exactly 0, that means in my model x2 does not have a effect. So effectively beta 2 equal to 0 means that you are dropping that, lasso solution is dropping that predictor from the model. So that's how it would be. So that is why lasso solution, it is like, you know, for state-wise variable selection, you are fitting each model, but here I am fitting only one model. Remember that I am fitting beta 1 x1, beta 2 x2, beta p xp. I am fitting one model with lasso penalty, and if it turns out suppose beta 2 equal to 0, beta p equal to 0, that means effectively I am dropping x2 and xp from the model, and I am obtaining the best fitted model by that. So in one shot I am getting the best model while dropping the predictors or the features which has no effect in the y, So this phenomena is called continuous subset selection. Now interestingly, Risdge takes care of the multicollinearity kinds of issue, and LASSO take care of the variable selection. So compromise between the Risdge and LASSO was given by Zhao and Hasty in 2005, known as elastic net penalty. They invented this elastic net penalty, which is essentially a convex combination of LASSO and Risdge and LASSO. You can see alpha has to be between 0 and 1, and they build this new penalty. So here is a extract from Tipshirani's book. So this is an example of LASSO, how the LASSO penalty would look like, and you see the LASSO penalty is very sharp, has a very sharp edges, and because of that the optimization technique. So this is typically the Bayesian interpretation. This is the posterior distribution. In Bayesian interpretation, what happens in classical statistics, we do all inference based using sampling distribution. In Bayesian inference, we do all the inference using posterior distribution. Here they have put a posterior distribution, and what you can see that for the LASSO, this posterior distribution is pulled so much that for beta 1 it includes 0. So the beta 1 does not have any effect, whereas because beta 1 can be somewhere in this region, but beta 2 is typically in this region, so beta 2 still have effect, but beta 2 does not. Whereas in this is the Risdge penalty is sort of a ball. It creates a ball effect. It doesn't create and because it's much more smooth, it does not pull the coefficient that much. So still it may touch, but it is not actually containing the beta 2. So Risdge penalty does not yield a sparse solution, but LASSO penalty yields a sparse solution. So what I mean by sparse solution? What I mean by sparse solution, if I have x1, x2, x3, and that means corresponding coefficient beta 1, beta 2 and beta 3, if any of them becomes 0, the solution itself will tell me that yes, it is exactly 0. That means automatically I am dropping that predictor from the model. If beta 2 and beta 3 turns out to be exactly 0, then I can automatically, the model itself is dropping and the final solution itself is dropping x2 and x3 and keeping only x1 beta 1 in the model. And as a result, LASSO can do that. So that's why LASSO penalty have a capability to yield sparse solution, but Risdge does not. Whereas elastic net has an interesting property, which is a convex combination of both Risdge and LASSO. So it do take care of both multicollinearity and variable selection, whereas Risdge do take care of the multicollinearity but cannot handle the variable selection. On the other hand, LASSO do handle variable selection but cannot handle the multicollinearity. Okay, so with this I have kind of summarize here. Risdge regression takes care of the multicollinearity. The paper, it was developed by Horrell and Kennard in 1970. Then 1996, LASSO regression, which takes care of the feature selection, and elastic net regression takes care of the both feature selection and multicollinearity. Okay, nice. All right, we will now resume some hands-on, and let's go to do some hands-on, and see you then. Take care. Bye.